Have you ever gazed up at the night sky and felt like there are secrets just, beyond the reach of even our most powerful telescopes? It turns out, even with our incredible instruments, our traditional cameras might be subtly holding back some of the universe's most dynamic and fleeting revelations. Today, we're taking a deep dive into a stack of really fascinating research, particularly a perspective paper called Neuromorphic Cameras in Astronomy, unveiling the future of celestial imaging beyond conventional limits. And this paper, well, it's got contributions from institutions like the Indian Institute of Science, the Indian Space Research Organization,
Yeah.
ISRO, right? And authors like Yadav, Bretan, Ajudia, Kumar, Roy, Van Schaik, Thakur. It really challenges our assumptions about, how we capture light from the cosmos.
It is, yeah.
Yeah.
It's truly a compelling vision. This technology aims to overcome some long-standing and frankly often frustrating challenges in optical astronomy. Our mission today really is to unpack how these new sensors, inspired by biology, actually function, what advantages they bring, and they're profound, and what they've already revealed about the universe, everything from distant stars to like objects passing right by our own moon.
Exactly. Think of this deep dive as your shortcut to understanding the next frontier in astronomical imaging. We'll uncover insights that might just change how you think about capturing light, revealing this entirely new way for observatories to see. Hmm. So let's start by looking at the foundations, how we've been observing the universe and why those methods are now sort of hitting their limits. For decades, charge-coupled devices, CCDs, and more recently, SCMOS sensors, that's scientific complementary metal oxide semiconductor, these have been the absolute workhorses of optical astronomy. These aren't just, fancy cameras. They're instruments that have given us unprecedented views, intricate planetary details, the delicate structures of faint galaxies, the incredible tapestry of the cosmos. We owe so much of our current understanding to these technologies, don't we?
We absolutely do, yeah. The evolution of these imaging technologies has profoundly shaped our ability to understand the cosmos, no question. From the earliest rudimentary telescopes to these incredibly sophisticated CCDs and SEMOS sensors, each innovation has allowed us to peer deeper with greater clarity, greater sensitivity. They've been instrumental in precisely observing and analyzing everything from the swift movements of asteroids to the dramatic, transient explosions of supernovae. These sensors truly set the stage for much of what we know today. They gave us those detailed images that fill our textbooks and, inspire new generations.
But even these incredibly sophisticated tools, as powerful as they come with inherent trade-offs,
Right.
limitations. What are the major headaches astronomers still encounter? The invisible walls we keep pushing against when we try to observe some of the universe's most interesting phenomena?
That's a crucial question. And while CCDs and SEMOS cameras have been revolutionary, yeah, their fundamental design principles revealed significant limitations, especially when astronomical phenomena push the boundaries of, say, extreme brightness, rapid change, or just the sheer volume of data.
Okay, let's talk about one of the most common frustrations about it, dynamic range, or maybe the lack of it. Imagine you're an astronomer trying to photograph a faint nebula, right? But there's a dazzlingly bright star right next to it, or worse, the full moon is just blasting light across the entire sky. Your traditional camera simply can't capture both the subtle glow and the intense brightness simultaneously. The paper points out that CCDs are often entirely unusable during full moon nights because that bright sky background completely overwhelms the pixels. It saturates them, essentially blinding the sensor to any fainter objects nearby.
Yeah, saturation. And this presents a perennial dilemma for observatories. How do you possibly capture the subtle glow of a distant, faint nebula when a nearby bright star, or the moon, completely overwhelms the sensor? Conventional sensors simply can't handle such diverse brightness levels. They either overexpose the bright areas, losing all detail, or underexpose the faint ones, making them invisible. It's often due to charge saturation, and this phenomenon known as blooming, where excess charge from an overexposed pixel spills over into adjacent pixels, creates streaks or blur across the image.
Right, that streaking effect.
Exactly. And while anti-blooming measures can mitigate this somewhat, the paper notes they often come at a cost, usually reducing the camera's quantum efficiency.
So it becomes less sensitive overall.
Precisely. It's a constant compromise between dynamic range and the ability to capture every single precious photon.
So it's not just about how bright or dim things are, but also how fast they're moving. Picture trying to photograph a hummingbird with a classic camera. You often get a blurry streak, right? Not a crisp image of its rapidly beating wings. Similarly, the fixed readout speed of conventional CCD and CMO sensors significantly curtails their effectiveness in detecting and characterizing rapidly changing or moving celestial objects. Both sensor types synchronize pixel digitization at a fixed frame rate, maybe 30 to 60 frames per second, typically, which means we're essentially taking snapshots at predetermined intervals. For anything truly dynamic, you're either getting motion blur or worse, entirely missing crucial, fleeting moments of action.
And that's a significant bottleneck for understanding the universe's most dynamic events, a huge one. If we consider the broader implications, this fixed frame rate means that phenomena like rapidly orbiting satellites, brief meteorite impacts on the moon, or the fast flickers of variable stars can be incredibly difficult, maybe impossible, to observe with the precision required. Current tech often resorts to specialized fast photomultiplier tubes for these dynamic phenomena, but those have their own limitations: field of view, spectral coverage. The universe doesn't pause for our camera's frame rate. So the need for sensors that can capture these events asynchronously, independent of a fixed clock, is crucial for getting more accurate, more detailed observations.
And then there's the sheer mind-boggling volume of data. Imagine being an astronomer, having to download and sort through mountains of data every single night, much of it just redundant background information where absolutely nothing of interest is happening. The paper highlights this as an incredibly challenging task. The Sloan Digital Sky Survey, SDSS for example, generates about 200 gigabytes of data nightly, and it just escalates dramatically. The upcoming Large Synoptic Survey Telescope, LSST, that's projected to churn out a staggering 200 petabytes a night. That's just an astronomical amount of information to manage, store, process. Most of it's static sky background. It's like trying to find a needle in a haystack where the haystack is continually growing, exponentially.
Yeah, this is a critical and often underestimated challenge. Storing and processing such immense volumes of data without any inherent compression is incredibly resource intensive. It demands vast computational power, huge storage infrastructure, places a massive burden on observatories. We urgently need imaging sensors that can intelligently output only the relevant information, minimizing redundant background data and focusing solely on what truly matters. The changes, the dynamics within the celestial scene. Otherwise, we're not just collecting data, we're quite literally drowning in it. Makes it harder to extract meaningful insights, even delays discoveries.
And to top off these technical and logistical challenges, we have new man-made hurdles. With the rapidly increasing number of satellites in low Earth orbit, our views of the cosmos are increasingly interrupted. Imagine setting up a precious, long-exposure observation, only for a satellite to streak through your field of view, completely saturating your conventional sensor for several minutes. That can ruin an entire observation session. Sometimes hours of painstaking setup and planning gone. The paper discusses how this degradation of the night sky from both light pollution and these satellite streaks poses a significant and growing threat to ground-based astronomy. It's like someone repeatedly flashing a bright light across your vision when you're trying to focus on something incredibly tiny and distant.
It's a very real and growing threat, yeah.
Yeah.
Capturing faint objects needs longer exposure times, and many observatories perform wide-field imaging to detect transient events. Both put them at higher risk from these satellite streaks. The risk is that these satellites can completely disrupt or even invalidate an observation for several precious minutes. This situation necessitates the development of, or maybe integration with, fast-acting wide-field cameras that can operate synergistically alongside the high-precision astronomical cameras. Such a system could detect an approaching satellite and then signal the main camera to momentarily close its shutter, protecting the observation.
Like a little guardian angel for the main camera.
Exactly. It's about protecting the integrity and continuity of our ground-based astronomical data.
Now, here's where it gets really interesting. This new generation of cameras, it isn't just about incrementally better pixels. It's about a fundamentally different way of seeing, inspired directly by biology. The paper calls it a paradigm change. So tell us, how exactly does a camera begin to mimic our own eyes to solve some of these really profound challenges?
What's truly fascinating here is the elegant biomimicry. It draws direct inspiration from the biological functioning of the human eye, specifically the retina. Each pixel in a neuromorphic camera is designed to operate much like the individual cells in our retina. A photodiode detects light that's analogous to our photoreceptor cells. Then a difference amplifier measures changes in light intensity, just like our bipolar cells process signals. And finally, comparators act like the on-off ganglion cells in our eyes, which generate events only when brightness changes across a certain predefined threshold. So rather than continuously streaming every bit of data, these cameras are specifically tuned to react to activity and change. Much like our eyes are incredibly attuned to motion and sudden shifts, rather than just static scenes.
So it's not taking a full picture, a frame every 30th of a second, capturing everything whether it's moving or not. Instead, each tiny pixel is telling us when and where a change happened. That's a huge philosophical shift from a typical digital camera. If a pixel sees a sudden increase in brightness, it sends out a +1 event with its location and precise time. If it sees a decrease, a maxifying event. It's essentially filtering out all the static, unchanging background information right at the source, isn't it?
Precisely. This core operational principle relies on several key mechanisms. First, incoming light is converted into an electrical current by the photodiode. This current is then transformed into a voltage that varies logarithmically with the light intensity. Think of it like a sophisticated audio compressor, but for light. It squeezes a vast range of light levels, from faint whispers to blaring shouts, into a signal the camera can understand. Makes subtle changes visible even when there's intense brightness nearby. Second, these events, represented as either +1 for increase or -1 for decrease, are generated only when brightness changes exceed specific temporal contrast thresholds. And crucially, after an event is generated, the pixel's internal reference voltage is immediately updated to the current log voltage, resets its sensitivity, preparing it to detect the next change. It's a continuous self-adjusting process.
And all of this happens independently for each pixel. So each pixel, rather than being part of a synchronized grid, autonomously broadcasts its exact location, x, y, whether it got brighter or darker, and the precise microsecond it happened. This is called address event representation, AER, right? And that's how all that incredibly time-sensitive information gets to the camera bus.
Exactly. And if we connect this to the bigger picture, this asynchronous, event-based approach means the camera isn't wasting precious resources on static information, it's only activated by dynamics. This dramatically reduces the data transmission requirements compared to conventional cameras that acquire information at that predefined fixed frame rate. That fixed rate is beautifully illustrated in Figure 1 of the paper with a fast rotating dot, often leads to significant motion blur in dynamic scenes. The neuromorphic camera, by only sending events when a change occurs, effectively mitigates motion blur and becomes incredibly efficient for capturing transient events with exceptionally high temporal resolution.
Okay, so what does this fundamental shift in how a camera sees actually mean for what we can observe in the cosmos? One of the biggest advantages you mentioned is its incredibly high dynamic range. This implies it can look at both extremely bright and extremely faint objects at the very same time without one washing out the other. For astronomers constantly battling the contrast between dazzling stars and dim nebulae, this sounds like, well, a dream come true.
It truly is a game changer. Yeah. What's fascinating here is how the neuromorphic camera achieves this remarkable high dynamic range, often exceeding 100 dB. That's significantly more than the typical 60 dB of standard cameras. When light intensity, which includes both constant background illumination and varying source brightness, is transformed into that logarithmic domain we discussed, these components get added up. But here's the clever part. Since the neuromorphic camera only detects changes in contrast, the constant background effectively cancels itself out. It just disappears from the output. This leaves only the variations in intensity due to the actual source. So that raises the question, how does that logarithmic processing make such a difference? Well, it allows the camera to compress this vast range of light intensities into a manageable signal, enables it to distinguish subtle variations even in extreme brightness conditions. This capability truly makes it excel at capturing faint objects like rocket debris or dim stars against an intensely bright background, like a full moon, where conventional cameras would be completely blinded by the glare.
That's a profound departure from how traditional cameras operate. The paper gives a fantastic visual in Figure 1G showing faint rocket debris and dim stars clearly visible right next to a brightly illuminated moon. A conventional camera just couldn't achieve that without either saturating the moon or losing the faint objects entirely. This implies we could, theoretically, be observing deep sky objects even on a full moon night, which is usually a complete write-off for many observatories. That's a massive unlock for precious telescope time.
Indeed. Beyond handling extreme brightness, there's the challenge of speed. Conventional cameras struggle with fast-moving objects, resulting in motion blur that makes precise measurements impossible. But these neuromorphic cameras offer microsecond-level precision. That sounds incredibly fast. How do they achieve such a rapid and precise response? Well, connecting this to the bigger picture, this high temporal resolution is absolutely crucial for characterizing dynamic astronomical events. Think rapidly rotating pulsars, fast-moving space debris. The asynchronous operation of each pixel, combined with event generation happening in the analog domain, allows the camera to capture dynamic scenes with exceptional responsiveness. Microsecond-level precision is that achieved through precise timestamping in the digital domain, usually facilitated by a fast megahertz clock. Imagine trying to track a rapidly moving satellite or even a meteoroid across the night sky. A conventional camera at, say, 30 or 60 frames per second gives you a blurry streak. Impossible to pinpoint the object accurately. But because each pixel in a neuromorphic camera operates independently and records an event with a microsecond-level timestamp the moment a change occurs, it captures those rapid movements with incredible clarity. The paper vividly shows how it tracks a fast-moving space station that's Figure 1G.6 without any motion blur, unlike its conventional counterpart in Figure 1G.5. It's about not just seeing that something happened, but precisely when and where it happened in that fleeting moment. Opens up completely new possibilities.
Okay, so if it's only sending data when something changes, rather than constantly streaming static frames, that must dramatically cut down on the sheer volume of data, right? No more drowning in 200 petabytes of mostly empty sky from the LSST. This sounds like a massive improvement for data storage and processing, which we just highlighted as a major bottleneck.
Absolutely. This event-driven data rate is a huge deal for data management, a game changer. Instead of continuously capturing full frames of a largely static night sky, which is what conventional cameras do, a neuromorphic camera remains silent in static scenes where no brightness changes occur. It only wakes up and transmits an event tuple, the x, y coordinates, polarity, brighter, darker, and timestamp when a pixel actually detects a contrast change. This makes it an incredibly efficient, data-driven sensor, only responds to dynamic variations. This intelligent approach means observatories no longer have to store vast amounts of redundant background data, significantly alleviates the massive storage and computational demands that plague traditional astronomy. It makes me wonder, how much more efficient can data acquisition become if we only record information that truly matters, rather than everything all the time? It's a much more intelligent approach.
And it's energy efficient too. Less power consumption means less heat generated, potentially less need for massive cooling systems. That seems like a monumental win, especially for long observations at remote observatories or even for future space-based telescopes where power and thermal management are always critical constraints.
It's a key advantage.
Yeah.
If we consider the broader implications, the operational benefits extend far beyond just data management. A conventional frame-based camera continuously samples the entire scene, leads to higher power consumption, elevates noise levels, generates significant heat, often needs bulky, energy-intensive cooling. A neuromorphic camera, however, has this minimalist event-driven approach. Each individual pixel consumes minimal power, a microwatt range, typically.
Yeah.
And crucially, only the parts of the sensor that are actively generating events actually use significant power. Makes its overall power usage much more efficient. For instance, the Professi Gen 4.1 camera discussed in the paper consumes around 500 milliwatt a total.
Wow, half a watt.
Compare that to CCD cameras, which can require 60-80 W just for cooling to manage noise. This reduced power consumption can significantly lessen the need for extra cooling hardware. A substantial benefit for long astronomical observations. Implies less infrastructure, less heat, potentially more compact, resilient designs. Invaluable for both ground-based and future space-based observatories.
Okay, so these cameras sound incredibly promising, almost like a silver bullet for many astronomical challenges, but no technology is perfect, right? Especially in its early stages. What are the current hurdles or limitations that still need to be addressed before neuromorphic cameras become truly ubiquitous across all observatories? What's the catch?
That's a crucial and very fair question. While neuromorphic cameras offer significant advantages, they do present several limitations, particularly in astronomy, at their current stage of development. Firstly, like traditional CMOS sensors, they use photodiode technology. Despite advancements like 3D stacking to enhance the photodiode area, their quantum efficiency currently peaks around 78% at 505 nanometers. Now, that's lower than many high-end CCD sensors, which can achieve over 95% quantum efficiency.
Okay.
So that makes CCD still the preferred choice for truly high-sensitivity observations, where every single photon counts, especially for capturing extremely faint static objects over long exposures.
So while they're incredibly good at dynamic scenes and high contrast, they're not yet the champions of capturing extremely faint high-resolution static images. And it's not just about collecting light, it's about making sense of it once you have it.
Exactly. Another current limitation is that neuromorphic cameras generally have lower pixel densities compared to traditional CCD and SCMOS sensors. This restricts their ability to capture very fine details, makes them less suitable for high-resolution imaging of intricate celestial objects where sharp static detail is paramount. And perhaps the most significant challenge for the astronomy community right now is the lack of standardized calibration techniques. Unlike CCDs and CMOS sensors, which benefit from decades of established procedures, bias frames, dark frames, flat field corrections, neuromorphic sensors operate on a fundamentally different principle. This means entirely new approaches are required to effectively address background noise, sensor artifacts, and response non-uniformity. So the natural next question is, how do we ensure the accuracy and reliability of the data from these novel sensors when our traditional calibration methods just don't apply?
So this implies astronomers can't just plug these in and seamlessly use their existing software and workflows. The paper explicitly points out that calibrating these event-based cameras is still an ongoing challenge without the established techniques astronomers are used to. It's like learning a whole new language for light.
Precisely. Furthermore, the number of events generated is directly determined by changes in contrast that exceed the pixel's temporal contrast threshold. Lower thresholds produce more events, higher thresholds reduce them. This dependence on the threshold significantly complicates accurate photometric measurements without a proper, well-understood model. And regarding noise, neuromorphic cameras have their own specific types. Imagine your camera sensors like a vast audience trying to hear a quiet whisper. Background activity is like a low, constant hum, air conditioning, people shifting. It's everywhere. It makes a whisper harder to discern, especially in low light, spatially uncorrelated. Then there are hot pixels. These are defective pixels acting like one person shouting, "Here I am," constantly, even when nothing's happening, draws your attention away.
Okay, that sounds annoying.
They are, often from manufacturing defects or heat. But because they're spatially fixed, they can potentially be detected and mitigated through new calibration or filtering techniques. So while powerful, they come with their own set of nuances that require new analytical frameworks.
This is really interesting. When we look at a star through a traditional telescope, we often see that fuzzy blob, a Gaussian blur, because of atmospheric turbulence, the telescope's optics. How does a neuromorphic camera see that same star, given its event-driven nature? It must be quite different, not just a blurred blob.
It's indeed a fascinating difference, and it highlights how these cameras resolve information in a completely new way. A conventional frame-based camera integrates all the incoming light over an exposure, effectively averaging out atmospheric tip-tilt variations, that rapid wobbling of the star's image due to our turbulent atmosphere. Results in the star appearing as a smooth, Gaussian-shaped intensity distribution, like in Figure 2A of the paper. In contrast, a neuromorphic camera doesn't average, it captures changes. It actually resolves these atmospheric tip-tilt variations as a continuous stream of distinct temporal events.
So it's not simply integrating away these small atmospheric perturbations over time like a conventional sensor, it's actually resolving them temporally, capturing the rapid wobbling of the star's image in real time.
Exactly. And because the greatest contrast changes happen at the edges of that blurred star profile, where the light intensity transitions most sharply from bright to dark, the events are primarily registered along the periphery. The uniform central region of the blurred star, which doesn't exhibit as much change, generates fewer events. So when you integrate these events and reconstruct the image, you get this fascinating donut-like appearance, as shown in Figure 2B, rather than the traditional Gaussian blob.
A donut star.
Pretty much. Importantly, the paper demonstrates that the flux obtained from this donut profile is directly proportional to that derived from the Gaussian profile, meaning the underlying scientific measurement of brightness remains sound, just represented differently. This really shifts our perspective on how atmospheric effects are captured. It's not a flaw, but a different representation of light, capturing the dynamic atmospheric effects rather than just integrating them away. Could open doors for new types of atmospheric characterization or even enhance adaptive optics systems.
It's one thing to talk about the technology, but what happened when they actually pointed these cameras at the sky? The researchers used two very different terrestrial telescopes to put the Prophecy Gen 4.1 neuromorphic camera through its paces, didn't they? One large and powerful, one smaller and more portable, testing its capabilities in varied real-world scenarios.
That's right. The choice of these two telescopes was very deliberate, allowed them to evaluate performance under various conditions and for different targets. For the large aperture observations, they used the 1300mm Devastal Fast Optical Telescope, DFOT, located at ARs in Devastal, India. High altitude, about 2,450 meters. Cassie grain design, narrow field of view, ideal for evaluating that high dynamic range on Bright stars, planets, the moon, star clusters.
So the big one for deep sky work, really testing that HDR capability in challenging conditions. The paper notes they specifically observed during a full moon night, usually a no-go for traditional CCDs to truly push this boundary. For the faster moving objects, they use a smaller 200 millimeter Dobsonian telescope in Bangalore, taking advantage of its wider field of view to catch things streaking across the sky. The paper goes into detail about the camera specs for the Prophecy Gen 4.1 5/80 by 720 resolution over 100 dB dynamic range, specific quantum efficiencies. Pretty impressive numbers.
Indeed. The 200 millimeter Dobsonian, a Newtonian reflector, wider field of view, 17.8 Yorick tenor, was perfectly suited for analyzing the high temporal resolution by observing rapidly moving objects. The observations with the DFOT were conducted on the full moon night of November 28, 2023, using Johnson V, B, and R filters to capture different wavelengths. The data acquisition involved converting the raw event data, those XYPT tuples, into grayscale images using a 2D histogram technique. This allowed them to then apply conventional astronomical analysis methods like abstract-photometry and astrometry, using existing tools like Astropy libraries and the GAIA DR3 database, a meticulous approach. And to fine-tune the camera for objects of vastly different brightnesses or speeds, they utilize IDAC bias setting.
IDC bias.
Think of it like an internal digital-to-analog converter that lets them precisely adjust the sensitivity thresholds of the pixels, almost like a very sophisticated per-pixel gain control, ensuring optimal detection whether it was a faint star or a dazzling planet like Jupiter, which they used for initial focusing and calibration.
Measuring the brightness of stars, photometry, is absolutely fundamental in astronomy. Helps us understand stellar properties, distances, evolution. So, how did the neuromorphic camera stack up against established data when it came to this crucial measurement? Did it provide consistent, accurate results, especially given the new way it sees?
Despite the novelty of the approach, the camera demonstrated impressive photometric capabilities. They conducted photometry on a star field containing Hiltner 600, analyzing 10 faint stars with V-band magnitudes from 10 to 16.25. The comparative results, shown in Figure 6 of the paper, clearly show a linear relationship between the computed flux from the neuromorphic camera and the true flux from the GIIA database for Johnson V, B, and R bands.
Okay, linear correlation. That's key.
Absolutely crucial for scientific measurement. While they acknowledge that varying IDAC bias settings can complicate comparisons across datasets, by carefully managing these, the error percentage between the computed and true star magnitudes remained consistently within 3%.
Only 3% error. That's excellent.
It really is.
Yeah.
Especially considering it was achieved without the standardized bias, dark, and flat field corrections that astronomers typically use, which, as we said, aren't directly applicable here. These initial results strongly suggest that with tailored methods, highly accurate photometric measurements are indeed within reach. Proves the feasibility of integrating neuromorphic data into established workflows.
That's fantastic validation. It means we can truly trust the quantitative data coming out of these new cameras, and this is where that high dynamic range we discussed earlier really shines. Imaging something like the trapezium cluster, super bright stars, right next to incredibly faint gas clouds, notoriously difficult. Conventional cameras often have to choose. Expose for the bright stars, saturates the gas, or expose for the gas, overexposes the stars. What did the neuromorphic camera reveal here? How did it manage this?
It's a monumental leap in capability. The trapezium cluster is indeed a challenging target. CCDs on moderate telescopes would typically need several minutes of integration, inevitably saturating the brighter stars. The researchers employed a clever, counterintuitive strategy. They used the neuromorphic camera on the DFOT, and rather than tracking statically, they actually slewed the telescope.
Slewed it, moved it while observing.
Exactly. This slewing motion, combined with atmospheric tip tilt effects, constantly creates subtle, detectable contrast variations, exactly what a neuromorphic camera is designed to detect. This allowed it to see the faint gas clouds more clearly, which a static, frame-based camera would just blur into obscurity. They successfully captured gas clouds and stars with V-band magnitudes ranging from 5.3 all the way down to 14.2 against the bright background of a full moon night. That's shown in Figure 7a. What's more, the gas cloud structures in their image showed a remarkable correlation with those seen in Hubble Space Telescope optical images. That's Figure 7b, a very strong validation.
That's absolutely fascinating. The slewing actually helps. It means we don't have to make that agonizing choice between seeing the dazzling heart of a cluster or the delicate tendrils of gas around it. We can have both. And the fact that it could pick out a magnitude 13 star right next to Vega, one of the brightest in the sky at nearly zero magnitude, and another faint star next to Betelgeuse, magnitude zero point 0.5, truly confirms that impressive 100 dB dynamic range claim. Conventional cameras would struggle severely to detect such faint stars within 4 arc minutes of those bright beacons, but the neuromorphic camera got them as close as 200 arc seconds from Vega and 170 arc seconds from Betelgeuse.
It's a testament to its unique design.
Yeah.
Now, let's talk about those fast-moving objects we discussed earlier. Satellites, space debris, maybe meteoroids, things usually just blurry streaks or entirely missed. How did the camera perform here?
So, how did the camera perform when faced with objects moving at incredible speeds, like the International Space Station, or even smaller, faster moving space debris? What kind of clarity could they achieve?
This really makes you wonder. What happens when objects move so fast, conventional cameras just can't keep up? Using the neuromorphic camera on the 200mm of Dobsonian in Bengaluru, the team successfully imaged objects like the ISS and the Atlas Centaur 2 rocket body, RB, achieving truly blur-free results. This was done by reconstructing the event data using only positive events at extremely short integration times, as short as 2 milliseconds.
2 milliseconds, that's like 500 frames per second equivalent.
Exactly, which effectively minimized motion blur. In stark contrast, reconstructions at a more conventional 16.67 milliseconds, or 60 fps, showed noticeable motion blur, as clearly depicted in Figure 8. This capability is critical because conventional cameras would have to significantly increase their gain to compensate for such short exposures, which dramatically increases noise, often obscuring the object even further. The neuromorphic camera brilliantly avoids this trade-off, delivering both speed and clarity.
So it's not just about getting rid of the blur, but doing it without introducing more noise. This means we can capture incredibly sharp details of objects in low Earth orbit, even with their erratic brightness changes. That's a huge step for space situational awareness, monitoring our increasingly cluttered orbital environment.
Indeed. And for something truly unexpected, they even caught potential meteoroids. Tell us about these serendipitous observations. What did they stumble upon while observing the moon?
That's one of the most exciting parts of this research. While conducting lunar observations with the neuromorphic camera, the researchers serendipitously detected light trails traversing the camera's field of view. This kind of event is incredibly difficult for conventional cameras to catch because lunar impacts typically appear as fleeting flashes of light lasting less than half a second, with speeds from 20 to 70 kilometers per second. Trying to capture those with fixed-frame video at, say, 30 fps often means they're completely missed or just a single blurry pixel.
This naturally makes you wonder about the frequency and distribution of meteoroid impacts across the solar system, right? The team analyzed the angular velocities of these light trails to determine whether they were meteoroids impacting the moon, maybe Earth-grazing meteors, or even satellites orbiting the moon. As shown in Figure 9 of the paper, the objects passing near the moon exhibited an average angular velocity of about 50 arc seconds per second. Corresponds to a linear velocity of about 100 kilometers per second near the lunar surface. Strongly suggests they are meteoroids. In contrast, other objects depicted showed significantly higher angular velocities, indicating they were passing much closer to Earth's surface. The ability of neuromorphic cameras to capture such transient and dynamic events, often missed by fixed-frame cameras, means we can gain far more accurate data on phenomena like lunar meteoroid impacts. It's an ideal application for a sensor designed for rapid changes. These observations from February 12th and 13th, 2024, provided precise sequences of events, with positive events in yellow, negative in blue, showcasing the camera's unique ability to see these fleeting blink-and-you-miss-them moments.
What a deep dive. We've seen how neuromorphic cameras, taking a cue from our own eyes, are really poised to revolutionize how we capture light from the cosmos. They offer this incredible combination of high dynamic range, microsecond level temporal resolution, and smarter data management, letting us literally see the universe in a whole new light. So, looking ahead, what's the grand vision for these event-based eyes on the sky? Where could neuromorphic cameras take astronomy next, beyond these initial impressive demonstrations?
The paper truly spells out a future where these cameras open up entirely new avenues of discovery. With their asynchronous operation, logarithmic processing, and unparalleled temporal and dynamic range, they've already proven their capabilities in real-world observations. This makes me consider, how can we best leverage these complementary strengths across the field? The potential for combining data from neuromorphic and conventional cameras is immense. They are particularly well suited for a wide range of applications, studying the incredibly rapid changes in binary star systems, capturing fleeting supernova-like curves with unprecedented detail, precisely characterizing asteroids and comets as they move through our solar system. Observing Jupiter's moon occultations with microsecond timing accuracy, continuously investigating meteorite impacts on celestial bodies like our moon. Beyond direct imaging, their high temporal resolution can critically support adaptive optic systems for real-time atmospheric correction and enhanced spectral imaging techniques, pushing the limits of ground-based observations even further. Furthermore, they are ideal for accurate timing measurements of pulsars and variable stars, where precise event timing is critical. By providing both a dynamic and static view of the cosmos, we create a far richer, more complete picture.
And crucially, we talked about satellite streaks being a huge and growing problem for traditional observations, ruining valuable telescope time. Can neuromorphic cameras actually help us solve that, acting as a kind of sentinel or guardian for our observatories?
Absolutely. This is a truly elegant solution to that growing problem.
Yeah.
The paper highlights that neuromorphic cameras can effectively address the challenge of satellite interference precisely because of their exceptionally high temporal resolution and event-driven nature. Imagine a neuromorphic camera equipped with a sufficiently wide field of view deployed as a dedicated guardian camera, constantly scanning for fast-moving objects. The very moment it detects an approaching satellite streak entering the observation path, it could send an immediate signal to a connected, conventional CCD camera, telling it to close its shutter for the brief period the satellite is in view.
Wow, real-time protection.
Exactly. This proactive detection and mitigation would prevent the conventional CCD sensor from saturating and corrupting valuable, long-exposure data, dramatically enhancing the reliability and continuity of critical night sky imaging. It beautifully illustrates how different technologies can synergistically improve astronomical research, turning a problem into an opportunity for intelligent observation.
So what are the next big steps? How do we take this incredibly promising technology from these initial groundbreaking findings to widespread use across observatories around the globe? What needs to happen for this paradigm change to truly take hold within the astronomy community?
The authors are very clear. This is a cutting-edge technology with significant, yet largely unexplored, potential in astronomy. While it's already proven its immense value in other demanding fields like robotics and automated vehicles, its transformative potential in astronomy is only just beginning to be understood. Their hope is that these preliminary findings will powerfully inspire the astronomy community to dive deeper, investigate further, and ultimately adopt this technology. The biggest hurdle, they emphasize, is still those specialized calibration techniques and the development of new algorithms specifically tailored for event-based data. This isn't just a tweak to existing systems. It's a fundamental shift that requires new tools and analytical frameworks to unlock its full potential. And if we consider the broader implications, this kind of innovation often requires a dedicated, community-wide effort to build the accompanying analytical frameworks. The development of robust calibration and specialized algorithms will be paramount in translating these initial promising results into widely adopted high-precision astronomical tools, ultimately transforming our ability to observe and interpret the dynamic universe.
What an incredible deep dive. We've journeyed through how neuromorphic cameras, drawing inspiration from our own amazing eyes, are poised to revolutionize how we capture light from the cosmos. They offer an unparalleled combination of high dynamic range, microsecond-level temporal resolution, and smarter event-driven data management, truly letting us see the universe in a whole new dynamic light.
Indeed. This exploration highlights how continuous technological innovation ceaselessly pushes the boundaries of what's observable. For you, the learner, it means understanding the new tools that will uncover the next generation of astronomical discoveries, from the fleeting glints of meteoroids to the most dynamic, evolving structures within distant star clusters.
So imagine a future where every observatory, every space probe is equipped with eyes that don't just see light, but precisely capture change itself. What rapid, transient cosmic events, entirely invisible to us now, might they finally reveal? What fundamental questions about the universe, questions we haven't even thought to ask yet, could we finally begin to answer?
That truly makes you wonder. If our perception of the universe has always been shaped by the limitations of our tools, how will a technology that literally sees in events rather than static frames fundamentally alter our understanding of cosmic evolution, the very nature of light, and the most dynamic processes within it? Something truly profound to ponder as you look up at the night sky tonight.